In this video, you'll learn about DC imperfections of op-amps. So far, we've primarily considered the op-amp to be ideal, but now we're going to consider some important non-ideal properties of the op-amp. Specifically, we're going to focus on its performance at DC, where it has a very large gain and is therefore subject to small imperfections. We're going to treat one non-ideality at a time. If we consider the output of an op-amp in response to a DC input voltage Vi, we would expect that at zero input voltage, we would have zero output voltage. Moreover, we expect that with small input voltages applied, we would see a large gain at the output. And of course, for large enough output voltages, we know that the op-amp output would saturate. Strictly speaking, this isn't an ideal op-amp, since an ideal op-amp would have infinite gain and no saturation, but this is certainly an op-amp without the DC imperfections that we're going to talk about next. Any real op-amp will have some offset. That means that with zero input voltage applied, we're not going to see zero output voltage. In fact, we'll see a finite positive or negative output voltage. We can't be sure which. Now, since the op-amp gain is so high, in most cases, not only will you see a finite output voltage, but it'll actually saturate. So in the example plot shown here on the right, the output voltage with zero input voltage has actually saturated at plus 10 volts. What we would find in practice is that if we sweep the input voltage, we can find one for which the output voltage does return to zero. In this case, that's at minus 5 millivolts. This is said to be the input offset of the op-amp. Around this voltage, if we make small changes in Vi, we would see the large gain that we expect. But because the gain is so large, it quickly saturates at the positive and negative voltages, in this case, plus 10 and minus 10 volts, respectively. In order to analyze op-amp circuits in the presence of DC offset, we need a model. Here's a suitable model that captures the effect of a finite DC offset. We see that inside of the model of the real op-amp, we've placed an offset-free op-amp. That is, an op-amp that's otherwise ideal with zero offset voltage. And then all we need to do to capture the effect of offset is place a DC voltage source, VOS, in series with one of the op-amp input terminals. The value of VOS is the input offset voltage. Which is precisely the voltage that we found on the last slide, provides zero output voltage. Indeed, we see that if we apply an input voltage VOS here, then we would have exactly 0 volts inside of our model applied to the offset-free op-amp. And since this dark blue triangle is offset-free, that would give rise to 0 volts at the output. So as we expect, at an input voltage of VOS, we have 0 output voltage. Now this is just a model of offset in op-amps. There's not really a DC voltage source in series with one of the op-amp input terminals. That's just how we capture its behavior. In reality, DC offset arises from any number of imperfections inside the op-amp circuit itself, small mismatches between the transistors that comprise it, for example. Since they arise from imperfections, the input offset voltage of an op-amp is not known precisely. Instead, op-amp datasheets will specify a range of possible input offset voltages. Typical values would be in the range of 1 to 5 millivolts, and the polarity is often not specified. Let's look at the impact of DC offset on a typical op-amp circuit, the inverting configuration. This will also give us practice doing analysis using the model of DC offset. Here's a standard inverting configuration. The op-amp here can be replaced by its model, including DC offset. So everything inside this triangle is just replaced by its model in order to capture the effect of DC offset. Now when we do that, the circuit would be driven by two sources, the DC offset source, VOS, and the input source, VI. We can then analyze the circuit by superposition, separately finding the circuit's output in response to VI and VOS. Now, the response to VI with VOS equal to 0 is simple. It's just the output of a regular inverting configuration. That is, VO equals negative R2 over R1 times VI. So here we're showing the analysis in response to the offset voltage source VOS by setting VI equal to 0. When we do that, we recognize that the output of the op-amp looks just like the output of a non-inverting configuration in response to an input source VOS. That is, VOS experiences the gain of the non-inverting configuration 1 plus R2 over R1. Now the complete output can be formed by superposition. That is, VO is the DC part in response to the input offset voltage VOS minus the desired portion that's in response to the input, negative R2 over R1 VI. So this term here represents a kind of a DC offset on the overall configuration. And it in turn depends on the offset voltage of the op-amp itself, VOS. Some op-amps come with special offset-nulling terminals, to which can be connected a potentiometer. The potentiometer can be adjusted, and doing so can introduce a canceling DC offset into the internal circuitry of the op-amp. So by attaching this potentiometer and adjusting it when the circuit's operating, we can zero out the DC offset inherent to the op-amp. That's why they're called offset-nulling terminals. But they're only available on some op-amps. Capacitive AC coupling is another way to mitigate the effect of op-amp DC offset on many op-amp configurations. For example, shown here is the inverting configuration again. Except here we've used capacitive coupling to attach the input VI to the input of the inverting configuration. Now, that capacitor voltage, that capacitance C can be made very large so that for any frequencies that we're interested in handling at the input, it essentially appears like a short circuit. And therefore, this circuit will, for all frequencies that we're interested in, behave essentially like a normal inverting configuration. However, no matter how large we make that capacitor, at DC, it's still an open circuit. So if we perform the analysis at DC, the input is completely disconnected. And we're just left with the simple circuit shown here. Again, we've replaced the op-amp with its model. that includes DC offset using the voltage source VOS. So the output of this circuit is easily analyzed. It's essentially a voltage follower configuration, so that the output VO is simply equal to VOS. That's much smaller than what we saw in the previous analysis without AC coupling, where we found that VO equals VOS times the gain of the non-inverting configuration, 1 plus R2 over R1. Especially in the case where we've designed the inverting configuration to provide a high gain, R2 over R1. So here again, we can form the total output by superposition. And it would be a combination of the DC output VO equals VOS plus the output in response to the input VI. So this technique can greatly reduce the impact of DC offset on the inverting configuration as long as we don't wish to amplify DC signals at the input. If we need to amplify DC signals, then we can't use AC coupling because remember that at DC, the capacitor is always an open circuit. And remember, the reduction in DC offset due to the AC coupling is especially significant when we have a large ratio R2 over R1, or a high gain from the configuration. Next, we'll consider a second DC problem encountered in op-amps, input bias current and input offset current. Remember that for ideal op-amps, we assumed that there was zero current into the input terminals of the op-amp. But many op-amps in reality require a small DC current to ensure their proper operation. This small input current is quantified in terms of its average which is called simply the input bias current, and the difference between them, which we call the input offset current. Typically, the polarity of the input offset current is unknown ahead of time, so just its absolute value is specified. Typically, the offset current would be in the range of 10% of the input bias current. These DC input currents will obviously affect the analysis of some of our op-amp configurations at DC. And input bias current and input offset current will have different effects. So let's consider the analysis of a closed-loop op-amp circuit taking into account the input bias currents. The configuration as it's pictured here is actually representative of both the inverting and the non-inverting configuration. In the inverting configuration, the input would be applied here. In the non-inverting configuration, the input would be applied here. But in either case, when we're considering the output in response only to the input bias currents, we would be setting the input source to 0. So in both cases, you end up with the same equivalent circuit. So let's proceed with the analysis. Here we're considering only the effective input bias current and otherwise assuming the op-amp is ideal. So that allows us to make use of the virtual ground assumption. So the negative op-amp input terminal is at 0 volts. That means that there's 0 volts across this resistor R1, and therefore 0 current flowing through it. But since there's an input bias current flowing into the negative op-amp terminal IB1, that current IB1 must be coming through R2, according to a simple nodal equation at this node. That in turn gives rise to a voltage drop across resistor R2, IB1 times R2. Since the voltage on the left side of the resistor is 0, that means the output voltage on the right side of the resistor is equal to IB1 times R2. So this is a finite output voltage in response to 0 input voltage that's arising purely due to the input bias current at the negative op-amp terminal. Now, there's a simple technique to reduce the effective input bias current, simply by introducing an additional resistor in series with the positive op-amp terminal. We're going to choose this resistor value so that a similar voltage drop arises due to the two input bias currents, IB1 and IB2. We can introduce this resistor R3 again in both the inverting and the non-inverting configurations. In the inverting configuration, the input would be connected here. In a non-inverting configuration, the input would be connected here. But now let's do the analysis of this circuit considering only the impact of the input bias currents. Now we saw that the current IB2 has to flow into the positive op-amp terminal. So that's going to give rise to a voltage drop across R3, which is equal to IB2 times R3. So the voltage at the positive op-amp input terminal is negative IB2 times R3. Since the op-amp is otherwise ideal, we're going to make use of our virtual short circuit between the two op-amp input terminals, and that tells us that the voltage here must also be negative IB2 times R3. Therefore, since there's 0 volts on the left side of R1, there's a voltage drop across R1 equal to negative, or equal to, with the polarity I've labeled positive, IB2 times R3, which in turn gives rise to this current flowing here, IB2 times R3 over R1. Next, we can make use of a nodal equation here. Which says that the sum of all those currents has to equal 0. So that will tell us that the current in this branch has to equal IB1 flowing this way minus the current flowing into the node through R1, IB2 times R3 over R1. So that then is the current flowing through resistor R2, which in turn gives rise to a voltage drop across it. Finally, the output voltage is equal to the voltage on the left side of R2, which is negative IB2 R3, plus the voltage drop across R2, IB1, IB2, R3 over R1 times R2. Now, if there's input bias current but no input offset current, then IB1 equals IB2. And in this case, if we solve for VO equal to 0, what it would take to make the output voltage equal to 0, we find that that's true if we select R3 equal to R1 in parallel with R2. You can convince yourself of that by simply substituting that value of R3 into this expression, and again, assuming that there's input bias current but no input offset current. So that's really the best choice we can make for R3. That will completely eliminate the effect of input bias current, but unfortunately, it will not eliminate the effect of input offset current. In that case, if we take R3 equal to R2 in parallel with R1, then we end up with an output voltage that equals IOS, the offset current, times R2. Now, in fact, since we don't know the polarity of the offset current, this just gives us the magnitude of the output voltage in response to the offset current. But remembering that the offset current is expected to be only 10% or so of the input bias current, this is a tenfold improvement in the output offset that results due to input bias current. And that improvement is because we've introduced the resistor R3 with this special value. In the proceeding, we considered the impact of input bias current on a DC coupled op-amp configuration. But what if the op-amp configuration is AC coupled, as shown here? We may introduce this AC coupling for any number of reasons. For example, we may have introduced it to mitigate the impact of DC offset voltage, as we discussed previously. So in this case, note that the input bias current IB1, being a DC current, must flow entirely through the resistor R2. So that therefore gives rise to a voltage drop at DC across R2 of IB1 times R2. Now, what we would like is to choose, in this case, R3 to have a value that gives the exact same voltage drop across this resistor. Now, if we neglect input offset current, consider only input bias current, then IB2 equals IB1, and we would want to select R3 exactly equal to R2. This would then give us a voltage here of negative R2 times IB2. The virtual short circuit assumption would tell us that this voltage is also at negative R2 times IB2. This is an analysis only at DC, of course, and at DC we don't have to consider the input VI because C is an open circuit. So in this case, the output voltage is the voltage on the left side of the resistor R2, negative R2 IB2, plus the voltage drop on R2, which is R2 IB1. And so clearly that is just R2 times the difference between the two input bias currents or the input offset current. Again, the input offset current is usually, its polarity is usually not specified, so this is just telling us the magnitude of the output voltage. So again, by choosing, in this case, R3 equal to R2, we've made it so that the output voltage depends only on the offset current, not the input bias current. And that's the best we can do in this case. So in general, the resistance R3 that should be connected in the positive op-amp terminal should be equal to the DC resistance seen by the negative op-amp terminal. That's a good way to think of it because it applies equally to the DC coupled case we considered previously and the AC coupled case considered here. Because here at DC, we have an open circuit looking that way, so we see only the resistance R2. Whereas in the previous analysis, we had to consider R1 in parallel with R2 at DC. Input bias current can have another subtle negative effect that we will illustrate by considering a non-inverting configuration with AC coupling at the input. So here's our non-inverting configuration. The input's going to be over here. And let's say we'd like to AC couple it. So you might think, well, let's just go ahead and put an AC coupling capacitor in here. The problem in this case is what happens when we consider the circuit at DC. Of course, at DC, the capacitance is an open circuit, so the equivalent schematic looks like this. There's simply nothing connected to the positive op-amp terminal. But in this case, where is the input bias current, IB2, coming from? It's got nowhere to come from. So what we would see in practice if we attempted this, if there's any finite input bias current into that terminal, that voltage would just wander until it eventually saturates at one of the rails, and the output voltage likewise would saturate at one of the rails and would no longer be able to amplify any input applied over here on the left side of the AC coupling capacitor. So the moral of the story is that both op-amp terminals always require a DC path to ground in order to carry that finite input bias current. So here's a more practical illustration of an AC coupled non-inverting configuration. The input applied here, the AC coupling is provided by capacitor C2, and in this case we need to introduce the resistance R3 to provide a path for that input bias current IB2. Now the value for R3 can be chosen based on the technique we described previously to minimize the impact of input bias current. So in this case, there's also AC coupling on the inverting terminal provided by C1. So we would choose the value of R3 equal to the DC resistance seen at the negative op-amp terminal, which in this case is simply R2. So then the resistor R3 provides both a DC path for the input bias current to flow, while at the same time minimizing the impact of input bias current so that the output only depends on the input offset current. The downside here is that at frequencies that we're interested in, the capacitor C2 appears like a short. And so the input resistance seen here at AC frequencies would be equal to R3, which is a finite value, and that sort of negates one of the main benefits of the non-inverting configuration, which was that it has a very high, ideally infinite input resistance. Of course, in general, op-amps will have both DC offset and input bias and input offset currents present simultaneously. So we can consider the analysis of a circuit separately by superimposing the impact of each of these one at a time. For example, for the circuit like this, we could first consider what's the impact of DC offset by introducing our model for DC offset. We're doing the analysis at DC, of course, so we can consider all the capacitors as open circuits. And we know that the output in this case is simply equal to VOS. Then we can consider what's the impact of input bias current. And to do that, we can now neglect input offset and just do a DC analysis of the circuit, considering the input bias currents, IB2 and IB1. And we know in this case that the output is depending on the input offset current. So the net impact of both DC offset and input bias current on the output is going to be the superposition of these two. Finally, we'll just point out some particularly harmful impacts of DC imperfections on the inverting integrator. So here we first consider the impact of DC offset on the inverting integrator. So we've got an inverting integrator configuration, and we've introduced our model of offset for the op amp. And we can see right away what happens. Just due to the input offset voltage, that is with VI equal to 0, we've got a DC voltage VOS at the negative op amp terminal thanks to the virtual short circuit assumption, giving rise to a DC current flowing through the resistor R. Here we're doing the analysis considering only the effect of DC offset, so therefore all that current is flowing through the capacitor C and getting integrated on it. So here's the current flowing in the resistor R. It's getting integrated over time on the capacitor C. And so the output voltage is simply the voltage on the left side of the capacitance, VOS, plus the time integral of that current on the capacitor. So in practice, what you see is that very, very quickly, the small input offset voltage gets integrated onto the capacitor C. Depending on the polarity of the offset voltage, the output would either ramp up or down until it eventually saturates at one of its output limits. A remedy for this could be to turn the integrator into a leaky integrator by connecting a small resistance R2, or a large value resistance R2, I should say, in parallel with the capacitance C. Next, let's consider the impact of input bias current on the inverting integrator. So that's what's illustrated here in the bottom right. And you'll see in this case, we've taken the measure of introducing a resistance R3 into the positive op amp input terminal, and we've chosen its value to equal the DC resistance seen by the negative op amp terminal. And in the case of the inverting integrator, again, we're doing the analysis here with VI equal to 0 to consider only the effect of input bias current. We see in this case a DC resistance of simply R in the negative op amp terminal. So that's the value we choose for R3. That'll set up a voltage drop across this resistance that's matched to the DC voltage drop across this resistance, neglecting any offset current. So the only difference in voltages here that might give rise to a small additional current is due to the offset current. So the offset current, therefore, flows through the capacitance C and gets integrated on it, so that the output voltage over time will simply be equal to the voltage on the left side of capacitor C, that is negative IB2 times R. That's this voltage drop here, plus the integrated offset current on the capacitance C over time. So, for example, depending on the polarity of the offset current, we might see over time that the output voltage just ramps up and eventually will hit the op amp's saturation limit and just saturate there. So effectively will be unusable. Again, a remedy here could be to introduce a large value resistance in parallel with C, but then this would make it a non-ideal integrator. It would turn it into a leaky integrator.